Hello students, welcome to Fund Scholar. So in the last class we have discussed the number system of class 9 CBSE board, and in that class we have discussed what the numbers are and also about the rational numbers. Okay, so we already studied that what rational numbers are, and we have learned that how we can place them into this P by Q form, where P and Q both are whole numbers and Q is not equals to 0. Okay, so from this class we are going to discuss about what are the irrational numbers. Okay, so just like the rational numbers, the numbers which we can't express into this P by Q form will be called as the irrational numbers. Okay, so a number S is called irrational if it cannot be written in the form P by Q, where P and Q are integers and Q equals to not equals to 0. Okay, examples: P whole to the power cube or root 2, P whole root to the power cube or root 2 pi 0.101100. So in the last class we have learned about the terminating decimal numbers and recurring, non-recurring and non-terminating decimal numbers. So this is non-recurring and non-terminating decimal numbers. So the fractions which can't be turned into a decimal number, or the fractions which have tends to become a non-recurring and non-terminating decimal numbers will be considered as an irrational numbers. Okay, there are infinitely many irrational numbers. The Pythagoreans proved that the Pythagoras proved that root 2 is irrational. Okay, but we can also prove this by placing a right angle triangle and placing root 2 here. Okay, so this is just a little step that how we can place root 2, and we will also learn about this in our upcoming slides. We can prove irrationality by contradiction, and we can locate irrational numbers on number line using Pythagoras theorem. Okay, so these are all the characteristics of irrational numbers. So we will just take a glance of it. Okay, so let's go to the next slide. Okay, so in the next slide, prove that root 2 is not a rational number. Okay, if any number is not a rational number, so we can tell that that number is a irrational number, right? So by using long division method, it is possible to find the value of square roots of any number. The steps of finding the value of root 2 is given below. Okay, here we already learned in our lower classes that we can find root of any number by division method. Just we have to pair them up and write it like this. Then we have to use the nearest root number to find its values. Okay, so this process will be called as the division method to find a root of any number. Okay, so just like if we have to find the root 2 like this one, so we can write it like this. Okay, or we can write it like this, right? So in the denominator position, 10,000 is 100 square. Okay, and in the numerator position there is 20,000, which can be written like this and will be paired and can be solved like this, right? So we can solve this, but the answer we will get, we'll see that it will be turning into a non-recurring, non-terminating decimal number, and whose value will be go on like this. Okay, so the number 2 can be written as 2.000 because we have already seen that 2 means that 2 point, there are so many zeros will be, and we also know that after point 0 don't have any kind of value. So step 2, take the perfect square which is below 2. So the perfect square below 2 is 1. Then write the number 1 in both divisor and quotient place and subtract 1 from 2, you will get the remainder 1. Step 4, next write down 2 zeros and write after 1 and take the decimal point after 1 in the quotient. Just we have did in the previous section, and you can also do it in your home, in your copy, just like this. Okay, so next slide. Okay, now step 5, now add the divisor part with the same number that this is all you know, that how can we find the root of any number by division method. That method they have just explained that method. In step 6, now again write down 2 zeros and repeat step 5. Finally, you get the quotient value as 1.141421, and this will also will be continued, and that will be approximately equal to 1.414, right? So this is the next process. Now we will go, yes, the process will be done like this. Okay, and you can see we have already remainder 3836, and this will also go on, and this number will be a non-recurring, non-terminating decimal number, so that we can say that because of its not being terminated, so root 2 can be called as an irrational number, or root 2 is not a rational number, right? Next. Okay, so when you will continue this process, you will get the decimal expansion of root 2 as like this, which is clearly non-terminating and non-repeating. Therefore, root 2 is irrational number. Okay. If you have watched the Life of Pi movie, in that movie, Pi or Pisin Molidor Patel, he wrote the value of pi like for almost like 500 terms. Okay, pi also has a value that is 3.14 and all, right? So pi will be also considered as an irrational number, okay, or not a rational number. Just like if we try to divide 22 by 7, the number will be like this, will be also a non-terminating, non-recurring decimal number, right? So pi is also a irrational number, right? Acha, yes, the next time we are, so in the next slide we have the same thing. Now we will have to watch a video.
Now we know that square root of 2 is an irrational number. If you It is never ending. Also, you will not find any pattern in the digits after the decimal. Hence, it's also called a non-recurring decimal. There is no pattern that occurs again and again. These kinds of numbers are called irrational numbers. Consider square root of 3 for instance. You will get its value as 1.732050 and so on. Even this decimal is non-terminating and non-recurring. So root 3 is also an irrational number. You can try calculating the values of root 5, root 6, root 7 or root 8. You will find that all of them result in non-terminating, non-recurring decimals. But wait, root 9 equals 3. This is a rational number. Yes, root 9 is not an irrational number. In fact, square root of any perfect square will be a rational number. But the square root of any number which is not a perfect square will always result in an irrational number. Here's the interesting part. If you know these 2 points well, you can even form an irrational number by yourself. Let's see how. We have to form a number which does not end and does not repeat any pattern. Something like 2.01001, 0001, 00001, and so on. Here, the number does not end and is also non-recurring. This means that there is no pattern that repeats forever. You can even have a number like 15.2349, 449, 4449, 44449, and so on. This is also irrational as it is non-terminating and non-recurring. Where does this concept help us? Say you're asked to find 2 irrational numbers between 1.23 and 1.25. Remember, 1.24 is incorrect as it's terminating. We need a non-terminating, non-recurring decimal. Yes, we know that 1.24 is between these 2 numbers. After 1.24, we can start writing 01, 001, 0001, and so on. That's one irrational number between these 2 numbers. Again, let's write 1.24, and this time we write 02, 002, 0002, and so on after it. That's your second irrational number. So to find irrational numbers between 2 numbers, just write a rational number between them and then add non-terminating, non-recurring digits after it.
So we have watched a video that what are irrational numbers and why do we need them. Okay, and we won't be seeing much videos. So this one I have played just because that this one is quite genuine and important one. So let's go to the next one. Okay, there is another video that representing root 2 in a number line. Okay, we have already watched that how root 2 can be transformed into a non-recurring, non-terminating decimal number, which proves that root 2 is not an irrational number, and which is a irrational number. Okay, so I won't be playing this one. So let's see that how can we locate root 2. You can just watch the videos if you need it in the app. So how can we locate root 2 on the number line? So represent root 2 on a number line. So to do this, we just have to take one unit as AB and one unit as BC. Then we have to find the hypotenuse of one unit each. So if this is a right angle triangle and one unit is base and one unit is height, so the hypotenuse will be root 2 unit. just like 1 square plus 1 square, and if we root it, it will be root 2, and we can place it in this point, just like this one. Okay, here from A to B, that is 1 unit, and from B to C, that is 1 unit. So the hypotenuse O to C will be root 2. So the root 2's position will be here, right? So by this process we can plot any irrational number into a number line, right? So let's go to the next one. Okay, they have already done this one, like different examples. Okay, and they have asked you that how can we place 3.8 into the number line. Okay, so how plot root 3 on a number line? Okay, if we will have to watch this video if we need it. So currently now I hope you won't need this one. Okay, using Pythagoras theorem we can write root 2 here and 1 here. You have to just choose the base and height carefully so that you can plot them. Okay, they have taken OP as root 2 units and BP as 1 unit. So OB square will be root 3 unit, and it will be placed like this. And we have already learned that where root 2 will lie, so this will be easy for us, right? So how do we plot 5, and this one will be easy. You have to just take 2 and 1 as the base and height. So yes, they have taken 2 and 1 as the base and height, and it will be possible. For the yes, they have done the same way for this. Okay, now how do we plot root 6 and root 7 on a number line? This one is also easy. All they have the videos. If you want to watch, you can watch them, but if you want to try it by placing, like writing down root 5, so 5 can be written as the root over 2 plus 1. This will be like this. If you want to try it with 6, so root over 6 can also be written like 4 and 2. So 4 and root 2. If you take 2 square plus root 2 square, so the answer will be 4 plus 2, and it will be root over 6. And if you having a question that why we will write root 2 as square, so root 2 into root 2 will give us value approximately as 2. Okay, so this is the funda that they are using it. Okay, so these are quite easy one. So let's go to the next, and they have taken root 5. Okay, you can also use root 5 as the base. So root 5 square plus 1 is giving us 6. So OD means 6, and OF will be root 6 that square. Okay, so root 7 will be the answer, right? Okay, next, how do we represent root x on a number line, part 1? Okay, so root x, so if I think that AB is equals to S, so produce AB to C. So BC will be 1 unit, bisect AC at D. So center will be D, semicircle, and it will be BE will be root over x. Okay, so let's watch this video. Okay, because this one maybe you are not understanding this or getting this right. So this one already been done. Yes, this.
that any number that can be plotted on the number line is a real number. Consider root 2. This is a real number which is irrational and it approximately equals this value. It's non-terminating and non-recurring. It's easy to plot a number like 1 or 1.5 or 7.35 since they terminate. But how do we plot this real number? It's simple. We just use a different technique. Let this be a part of the number line. We have 0, 1 and 2 plotted on it. We know that this distance is 1 unit. Now let's draw a 1 unit length perpendicular at this point like this. This distance is the same as this distance. Both equal 1 unit. If we draw a segment like this, we get a right angle triangle. By the Pythagoras theorem, the hypotenuse squared will equal this squared plus this squared. Since both are 1 unit long, the hypotenuse squared will equal 1 squared plus 1 squared, which equals 2. Since the hypotenuse squared equals 2, the hypotenuse will equal root 2. This is the length we wanted, root 2. Once this is done, we can just keep the vertex of the compass at this point and cut an arc which cuts the number line. This distance will equal this distance as both are radii of the same circle with this center. So this distance will equal root 2. That's how we plot root 2. We do not measure the length and plot it. We form a triangle in such a way that we get root 2 as the hypotenuse. In a similar way, we plot root 3, root 5 and so on. To see these constructions in detail, please watch our videos on plotting irrational numbers on a number line. Now here's another interesting question. How can we plot a real number like square root of 3.8? We cannot form a right triangle with root 3.8 as the hypotenuse. There's another technique which we will look at in this second part of the video.
So from this video we have learned that how can we use Pythagoras theorem to represent any root like root x on a number line, and this video has two more extension part, but we won't be seeing this right now. So let's, yes, there is another process, that is semicircle method, but that process is a bit lengthy, and that is and you can watch the video and you will see that that is a little bit lengthy process, and that's a little bit harder one. So it will be better that if we stick to only Pythagoras theorem method. Okay, and it has also another method that will be like elliptical method. You can watch the video. Ellipse is not included in your syllabus, so I won't be discussing that. Okay. So let's go further. So can we find infinite rational numbers and infinite irrational numbers between any two rational numbers? Okay, just think it a bit and try to answer me. The answer will be yes. Yeah, the answer will be yes. So let's go to the next slide. Can we add, subtract, multiply and divide irrational numbers also? Then try to think about it and tell me. It will also be yes. Okay, and how this answer will be? So you will have to learn in further. Just like for root over AB, these all are just some formulas for so that we can calculate it further. So root over AB will be considered as root over A and root over B. Okay, and root over A by B will be root over A by root over B. Root over A plus B into root over A minus B will give us will give us A minus B, and a plus root b, it will be just the simple formula of a square minus b square, and also this will be a formula of a plus b, and that's whole square. And this is also root a minus root b, that's whole square will be a minus 2 root ab plus b. Okay, let's go to the next one. Okay, so here they have given us some simplification, simplify each of the following expressions. Okay, so another you all guys can try it at your home, but let me do number 3 for you. Okay, so it's just a simple formula of root 5 that square plus 2 into root 5 into root 2 and plus root 2 that square. So the answer will be 5 plus 2 root 10 plus 2. So the answer will be 7 plus 2 root 10. Right. So we have another video, but I am skipping this right now. Okay, rationalization of denominator. Okay, rationalization of denominator is a process of multiplying the denominators conjugate to both numerator and denominator to make the denominator as a rational number. Okay, so what they are trying to say, so let's look at this. Okay, so for all these cases we will just multiply 1 by root 2 in denominator to the numerator up, in numerator in up and denominator in down. So it will be look like this, yes, and it has become a rational number. Okay, and this will also follow for the next processes, just like we have to multiply like this to make it a rational number or make it look like a rational number. Okay, the same process will be applied in number 3 also. Okay. So what is the rationalizing factor or conjugate? Okay, and one thing that conjugate means for this number. So this number, the conjugate will be like this. The conjugate of this number will be this. The sign will get changed. Okay, and for this one the conjugate will be the same number itself. For this one the conjugate will be root over 7 plus root over 3, right? So these will be the answers. Okay, so now rationalizing factors. The rationalizing factor of root 3 will be 7 because it will be multiplied in the upper position and it will be giving us these numbers. Okay, so for this case, just like we have already solved in the previous slides, so to solve this one we have to just multiply the conjugate of this to make it look like a rational number. So minus 4 will be the answer, and rationalizing factors will be root 3 plus root 7, okay, or conjugate. So it will be the conjugate or rationalizing factors, just I have already told it before. Okay, the next one, the rationalizing denominator will be, the denominator will get multiplied in both upper and lower position, so it will be a rational number, just like we have discussed. Okay, these all will be like this. This is the conjugate, we will be multiplying both upper and lower position to make like this. Okay. Okay, writing nth root of a in exponential form. So there is a video. So this video will be a little beneficial. So let's play it.
In this video, we will look at real numbers in a different way. But first, let's review what we have learned until now. What's the square root of 64? We know it's 8, but how do we get an 8? We write 64 in terms of its prime factors. We write it as square root of 2 times 2 times 2 times 2 times 2 times 2. 6 2's under the square root. To find the square root, we just make groups of 2 same numbers and choose one from each group. In this case, we can make 3 groups like this. We choose one number from each group and remove the square root sign. Hence it will equal 2 times 2 times 2, which equals 8. What about cube root of 64? Doesn't matter if it's a square root or a cube root or the fourth root. The basic concept remains the same. We reduce the base to its prime factors and make groups of as many numbers as the index. So first, we write this as cube root of prime factors of 64. Since the index is 3, we make groups of 3 and choose one number from each group. Hence, this will equal 2 times 2, which equals 4. So this is the basic concept of roots. We reduce the base to its prime factors and make groups based on the index. Now let's understand a few terminologies. Consider 2 raised to 3 or 2 cubed. 2 is called the base and 3 is called the exponent or the power. Here, there is no root. This equals 2 multiplied by 2 multiplied by 2. Now consider the cube root of 8. We see a radical here. The number 3 is called the index or the order. And the number 8 is called the radicand or the base. We will refer to it as the base. This is called the third root of 8. For some reason, many students fear the radical sign. Wouldn't it be better if we could just write this without the radical sign? Since 8 is the base, we can write this as 8 raised to something. But what is that something? Let's see. Cube root of 8 can be written as 8 raised to 1 by 3. So we got this in the base and exponent form without the radical sign. We have 1 by 3 as the power. The power is actually the reciprocal of the index. The index was 3 and the power is 1 by 3. Similarly, the fourth root of 16 can be written as 16 raised to 1 by 4. The index was 4 and without the radical sign, we keep the base same and write the power as reciprocal of the index. And what about root of 256? When the index is not written, it means that's the square root. The index is 2. Hence, this equals 256 raised to 1 by 2. Doesn't matter what the index is, this will always be true. Even the 700th root of 1594 can be written as 1594 raised to 1 by 700. How does this notation help us? Of course, we eliminated the radical sign, but there are plenty more reasons why this notation can really help us. Try solving cube root of 3 multiplied by square root of 3. You would be slightly confused, but let's write it as 3 raised to 1 by 3 multiplied by 3 raised to 1 by 2. This looks comparatively simpler. We know that a raised to m multiplied by a raised to n equals a raised to n plus n. Same base writing it this way makes it easier to use the laws of exponents. Let me ask you another question. Look at these three numbers. 5th root of 6, 4th root of 8 and 6th root of 5.5. Arrange these in descending order. Just by looking at the numbers, you cannot compare them. Writing this in base and exponent form will also help us in comparison of such numbers. We will see how we can compare such irrational numbers in a separate video. So the main takeaway is that the base and the exponent form helps us in using the laws of exponents and in comparison of irrational numbers.
Okay, so we have learned that nth root of a in exponential form. How can we write nth root? Just like if I tell you to write this one, and if I tell you to write this one. So how can we write? So this was the topic of this video. So let's go to the next one. Okay. Acha. Every whole number is a natural number. Is it right or wrong? Is it right or wrong? This one is quite easy. It will be no. Every whole number is a natural number. It's no, because 0 is a whole number which is not a natural number. Okay, because we can't just count 0 in nature. We can just tell that anything which is empty can be termed as 0 in mathematics, but 0 is not a natural number. Okay. For example, if this is a cube, and a cube has 1, 2, 3, 4, many like 6 surfaces. Okay, so if I tell you that a cube has how many cones? So cube does not have any cone. Yes, it has edges, but it won't be termed as a cone, right? So a cube has 0 cones. So for that case, we can tell that cube has a 0 cone, but we can show it by any means. So that means that will be 0. But if I tell you that how many cones does this whatever is this, this will be like a pyramid. This pyramid has, obviously it will, you will tell that this is a triangle, but this is not a three-dimensional figure of triangle will be termed as a pyramid. Okay, so how many cones does this pyramid have? So the pyramid has 1 cone, we can show it. Okay, but for cube we can't. So let's go to the next one. Every integer is a rational number. Is it yes or no? You think and tell me. It will be yes. Every integer is a rational number, because every integer, be it -3, be it 0, be it 1, be it 100, or be it -1, or be it -100. Every number can be termed into p by q form like this. Okay, so that means that every integer is a rational number, right? Next, every real number is an irrational number. Okay, just think it carefully and try to answer. The answer will be no. Obviously it will be no, because every real number is an irrational number. No, but every irrational number is a real number. Okay, the reverse is right. Every irrational number is a real number, just I have told it before. The answer will be yes. Every irrational number irrational number means those numbers which can't be expressed into the P by Q form, which can't be expressed in this P by Q form. Okay, so they will be called as irrational numbers, but that irrational numbers can be termed into real numbers. Okay, so the reverse will be right. So let's go to the next one. Every point on the number line is of the form root m, where m is a natural number. So think it carefully and try to answer. The answer will be no. Every point on the number line is of the form of root m, where m is the natural number. It can't be correct. Okay, so if I try to explain it, so it will be like every point, just like we can draw this point, for this one this will be true, but if we write this number, the answer will be 3, which is a natural number. Okay, so for all cases this is not right, for some cases it is right. So from this we can tell that every point on the number line is of the form root over m is not a correct statement. Okay, so let's practice some questions. So these are like all will be easy. Convert the following rational numbers into decimal forms. Okay, so I am doing some of it and the rest of will be your homework. Okay, for like the first one and the fourth one. For this first one, we will have to just write 26 and then start pointing out from the last or from the end, and we have to just displace the point 4 digits earlier. So it will be 0, 0 to 6, right? If you are not understanding the 6 here, it will be here. Okay, and for this case we can just divide 84 and 700 and write it like this, and can write it down like this. Okay, right. And the rest of 2 will be your homework. Okay, and for these cases you have to divide 33 with 26. Okay, and here you can just convert it like multiply 19 into 4 plus 5 and then 19. Okay, and then you can do the rest of the part. Okay, let's go to the next one. Yes, the answers will be like this. And examine whether the following numbers are rational or irrational. For this case, okay, these will be all as the first one, the 7. The 7 is an irrational number. Why? Because it will be termed into the value of root 7 will be a non-terminating, non-recurring decimal number. So the root 7 is an irrational number, and for the rest of the cases will be maybe not. Okay, because root 3 plus root 5, the value of this we can just term it into like, we can term it yes, we can write it down and and solve it down. Yes, it will be a rational number, irrational number. And for this case we can just solve it like this and can find the answer. And for these cases we we'll have to solve it just by multiplying it, and for the fifth one we'll have to apply the a plus b and that's whole square formula of it. Okay. So the first one will be rational, the second one will be irrational, third one will be irrational, fourth one will be rational, and fifth one will be irrational. Just like I have told that first one will be rational, the second one you don't have to follow the whole process. If they have asked you that whether it's rational or irrational, you can just do it by like doing 2 or 3 steps, and for the third one it will be irrational once again, the fourth one will be rational. Okay, and how it's becoming rational? So 2 root 2 minus 4 plus 2 minus 2 root 2. So these two numbers will get eliminated and the answer will be minus 2. So this is a rational number. So that's why this one will be rational. And for this one, if it follows the formula of 3a square plus b square plus 2ab, so the answer will be like this, and here we have root 6 which is an irrational number. So that's why the whole number will be rational, right? Okay, give an example of each of two rational numbers whose difference is a rational number. Okay, so they have asked us that 3 minus 2 is 1. So this one will be an easy example of this. Difference is an irrational number. So difference is an irrational number, like root over, like any two root numbers, like root over 2 minus root over 3. The answer will be irrational. Okay, sum is a rational number. The same option can be the same example, we can also give that, and sum is an irrational number. This will also be a same example. Okay, product is a rational number. So the product, this will also be the same, like 3 into 2 gives us 6. So the product is the rational number. So product is an irrational number, just like this one. Root 2 into root 3 will give us root 6, which is an irrational number. Quotient is a rational number, just like the same. I mean, if you apply all this, all 8, quotient is an irrational number. This all 8 examples can be given just by like root 2 and root 3 and 2 and 3 itself. Yes, they have also did like this, like they have also taken root 3 and root 2 and 5 and 2. Okay, these all can be done with just like for 2 and 3 examples. Okay, find 3 different irrational numbers between 5 by 7 and 9 by 11. Okay, so to solve the sum, to solve the sum we will have to just find the value of 5 by 7, okay, which is nearest, like which will be like this, and 9 by 11 will be like so, and just try to put a root number in between these two numbers to find root over 52, which will be the same value as root over 72, so which is greater than 0.71 and lesser than 0.8. Okay, this one will be a quite easy one. Okay, find the value of root over 0.2222 bar. This is a recurring decimal number. Both are recurring decimal numbers. So by this process, we have already learned in the last class that how we calculate the recurring numbers or recurring decimal numbers in this process. So they have already done it. X equals to, we have to let that x equals to this one, then 100 is equals to this, Now we have to just subtract it and then find the value of it. Okay, the same process we will also apply the same process in the rest of the one, and the answer will be 5 by 11, right? Okay, so what did we learn? So we have already learned that what are the rational numbers, what are the irrational numbers, and how can we term rational numbers into p by q form, and how irrational numbers can be placed in the number line, and decimal numbers, also the recurring decimal numbers. So thank you guys, and I am signing off this class. Hope you have enjoyed the class. Thank you very much.